Most days, we step outside and feel the weather without really noticing it. The air is warm or cold. The sky is clear or heavy. And it all seems simple on the surface. But above us, an immense system is always in motion. Invisible currents are shifting. Energy is being exchanged. Water is quietly changing form. All part of a continuous process that shapes every day we experience. In this video, we will move slowly through that system. From sunlight to wind, from clouds to storms, and begin to see weather not as isolated events, but as a connected whole. Let's begin at the source. The energy that sets everything in motion. When we talk about weather, we are often describing something immediate, something we can feel on our skin or see when we look up. The warmth of sunlight, the weight of humidity, the movement of wind, the presence or absence of clouds. These small observations are where understanding begins. Not with complexity, but with attention. Weather is the condition of the atmosphere at a specific place and at a specific moment. It changes hour by hour, sometimes minute by minute. It is local, and it is temporary. This is why weather can feel unpredictable, because it is always in motion, always adjusting. But weather is not random. It follows physical rules, even when those rules produce complex patterns. To understand weather, we begin by separating it from a related idea: climate. Climate is not what is happening right now. Climate is the average pattern of weather over long periods of time, often measured in decades. If weather is a single day, climate is the memory of many days, layered together. A rainy afternoon does not define a climate, but many rainy seasons begin to form one. A sudden cold day does not define a region, but long winters begin to shape expectations. This distinction is simple, but it is important, because it helps us place each moment into a larger context. Weather is what we experience. Climate is what we expect. Both are connected, but they are not the same. When we return to weather itself, we can begin to see it differently. Not as isolated events, but as expressions of a system. The atmosphere is that system. It surrounds the Earth and extends upward for many kilometers. It is made of gases, mostly nitrogen and oxygen, with smaller amounts of other components, including water vapor. This thin layer of air may seem still, but it is always moving, always adjusting to changes in energy. It behaves in some ways like a fluid, like an ocean that flows around the planet. But unlike the ocean, it is invisible to us most of the time. We do not see the air directly. We see its effects. Clouds forming, leaves moving, rain falling. These visible signs are the surface of deeper processes. At any moment, the atmosphere is balancing differences. Differences in temperature, differences in pressure, differences in moisture. These differences are small in isolation, but together they create motion. And that motion becomes weather. When air warms, it expands and becomes less dense. When air cools, it contracts and becomes more dense. This simple behavior creates vertical movement. Warm air tends to rise. Cool air tends to sink. This rising and sinking happens constantly, across different regions, at different scales. At the same time, air moves horizontally, flowing from areas of higher pressure to areas of lower pressure. This horizontal movement is what we feel as wind. Wind is not separate from weather. It is one of its basic expressions. Temperature, pressure, and moisture. These are the core elements. They interact continuously, and their interaction creates patterns. Some patterns are gentle, a light breeze, a gradual change in temperature. Others are more intense, strong winds, rapid shifts. But the underlying principles remain the same. It can help to think of the atmosphere as a system that is always seeking balance, but never fully reaching it. Energy enters the system, mostly from the sun, and that energy is unevenly distributed. Some areas receive more, others receive less. This uneven distribution creates differences, and those differences drive motion. The system responds by moving air, redistributing heat, cycling water. But because the input of energy continues, the motion never stops. This is why weather is always changing. It is not moving towards stillness. It is maintaining a dynamic balance. Another way to understand this is to observe patterns over time. A clear morning may become cloudy. Clouds may thicken into rain. Rain may pass and leave clearer skies again. Each stage is connected. Each stage follows from the one before. Nothing appears without cause, even if the cause is not immediately visible. The atmosphere carries information forward in the form of temperature, moisture, and motion. This is why weather forecasting is possible, though never perfect. Small differences can grow over time and lead to different outcomes. But the underlying structure remains governed by physical laws. When we observe weather, we are observing the result of many interacting processes. Some occur at large scales, across continents. Others occur at small scales, within a single cloud. All of them contribute to what we experience at ground level. This layered complexity can seem difficult at first, but it becomes clearer when we return to simple principles. air moves. Because of differences. Water changes form. Because of temperature. Energy flows. Because of imbalance. These ideas repeat across every type of weather. By holding on to them, we can begin to understand more complex patterns without losing clarity. It is also useful to notice that weather is not separate from daily life. It shapes how we move, what we wear, how we build. It influences ecosystems, agriculture, and water availability. But in this space, we are not focusing on its impact. We are focusing on its structure, on how it works. Slowly, step by step, as we continue, we will move deeper into the atmosphere itself, not just as a concept, but as a layered environment, a place with structure, boundaries, and distinct regions. Understanding those layers will give us a clearer foundation for everything that follows. Let us begin by looking upward into the vertical structure of the air above us. Above us, the atmosphere is not uniform. It is arranged in layers. Each layer has its own structure, its own behavior, and its own role in shaping weather. These layers are defined by how temperature changes with height, not by visible boundaries. There are no sharp lines in the sky, only gradual transitions. We begin with the lowest layer, the troposphere. The troposphere extends from the surface of the Earth to an average height of about 8 to 15 kilometers. It is thinner near the poles and thicker near the equator. This is where almost all weather occurs. Clouds form here. Rain falls here. Winds move here. The air in the troposphere contains most of the atmosphere's mass and nearly all of its water vapor. This makes it the most active layer. Within the troposphere, temperature generally decreases with height. This is a key pattern. As you go higher, the air becomes colder. This temperature decrease drives vertical motion. Warm air near the surface rises. Cool air above sinks. This continuous movement allows mixing and supports cloud formation. The top of the troposphere is called the tropopause. It acts as a boundary, but not a solid one. Here, the temperature trend changes. It stops decreasing and begins to stabilize. This change limits how far rising air can travel. Most weather systems remain contained below this level. Above the tropopause, we enter the stratosphere. The stratosphere extends from about 10 to 50 kilometers above the surface. It is more stable than the troposphere. Here, temperature increases with height. This is the opposite pattern. This increase is caused by the absorption of ultraviolet radiation, by ozone. Ozone is a form of oxygen, concentrated in a region often called the ozone layer. As ozone absorbs energy, it warms the surrounding air. This creates a stable structure, where vertical movement is limited. Warm air sits above cooler air, reducing mixing. Because of this stability, clouds are rare in the stratosphere. Most weather does not reach this layer. However, the stratosphere still plays an important role. It influences large-scale circulation and helps protect life by filtering harmful radiation. The boundary at the top of the stratosphere is called the stratopause. Again, this is where the temperature trend changes. Above this, we move into the mesosphere. The mesosphere extends from about 50 to 85 kilometers. Here, temperature once again decreases with height. It becomes one of the coldest regions of the atmosphere. The air is very thin, much less dense than in the layers below. Weather, as we experience it, does not occur here, but this layer is still active in other ways. For example, many meteors burn up in the mesosphere due to friction with air particles. This process produces brief streaks of light, visible from the ground. The top of the mesosphere is called the mesopause. It marks another shift in temperature behavior. Above this, we enter the thermosphere. The thermosphere extends from about 85 kilometers upward, often to several hundred kilometers. In this layer, temperature increases sharply with height. This is due to the absorption of high-energy radiation from the sun. However, the air is extremely thin, so this heat would not feel warm in the usual sense. The thermosphere contains very few particles, spread over large distances. This layer is where phenomena like auroras occur, caused by interactions between solar particles and Earth's magnetic field. Above the thermosphere, the atmosphere gradually transitions into space. This outer region is sometimes called the exosphere, where particles can travel long distances without collision. But for understanding weather, our focus remains lower, especially within the troposphere. The layered structure of the atmosphere is not arbitrary. It reflects how energy is absorbed and transferred. Each change in temperature pattern creates a new layer. These layers influence how air moves and how energy flows. For example, the decreasing temperature in the troposphere encourages mixing, while the increasing temperature in the stratosphere suppresses it. This contrast is essential. It helps contain weather near the surface. If the entire atmosphere mixed freely, weather patterns would be very different. The boundaries between layers also shape movement. Rising air slows near the tropopause. Horizontal flows can become stronger near these transitions. One example is the jet stream, which forms near the boundary between the troposphere and stratosphere. These fast-moving air currents influence weather systems by guiding their paths. Even though we do not see these layers directly, their effects are present in daily weather. The height of clouds, the development of storms, the movement of air masses, all are shaped by vertical structure. It can be helpful to think again of the atmosphere as an ocean, but one with layers of different temperatures. In some layers, mixing is easy. In others, it is limited. This layered behavior creates patterns over time, and those patterns become the foundation of weather systems. Another important aspect is pressure. As altitude increases, air pressure decreases. This is because there is less air above pressing down. Near the surface, pressure is higher. Higher up, it becomes much lower. This gradient affects how air expands, cools, and moves. Rising air expands as pressure drops, and this expansion causes cooling. This cooling is a key part of cloud formation. It connects vertical structure to visible weather. In this way, the layers are not separate systems. They are connected through continuous physical processes. Understanding these layers gives us a framework, a way to organize what might otherwise seem complex. Instead of seeing weather as isolated events, we begin to see where those events occur and why they remain within certain boundaries. This perspective is steady and repeatable. It allows us to move forward without losing clarity. As we continue, we will focus on the source of energy that drives all motion within these layers: the uneven heating of the earth by the sun. At the center of all weather, there is a steady source of energy: the sun. It provides the heat that drives motion in the atmosphere. Without it, the air would remain largely still. There would be no wind, no clouds forming, no cycles of change. The sun's energy arrives at Earth in the form of radiation. It travels through space and reaches the surface. Some of this energy is reflected back into space by clouds, by ice, and by light-colored surfaces. The rest is absorbed, mostly by land, oceans, and the lower atmosphere. This absorbed energy becomes heat, and this heat begins to move. But the heating is not equal across the planet. This is the key idea. The Earth is curved, and it is tilted on its axis. Because of this, sunlight does not strike all areas in the same way. Near the equator, sunlight arrives more directly. It is concentrated over a smaller area. This leads to stronger heating. Near the poles, sunlight arrives at a lower angle. it is spread over a larger area. This leads to weaker heating. This difference creates a temperature gradient from the equator to the poles. It is one of the main drivers of atmospheric motion. Energy moves from warmer regions toward cooler regions. This movement does not happen instantly. It happens through air and water, through currents, through circulation. In this way, the atmosphere works to redistribute energy. It reduces differences, but it never removes them completely. This ongoing imbalance keeps the system active. Another important difference is between day and night. When a region faces the sun, it receives energy. When it turns away, it begins to lose energy. During the day, surfaces warm. During the night, they cool. This daily cycle creates smaller temperature changes, layered on top of the larger global pattern. Land and water respond differently to this heating. Land heats up quickly and cools down quickly. Water heats more slowly and cools more slowly. This difference creates local contrasts, especially near coastlines. During the day, land may become warmer than the nearby ocean. Warm air rises over land, and cooler air moves in from the water. This creates a sea breeze. At night, the pattern can reverse. These are small examples, but they follow the same principle. Uneven heating leads to movement. The angle of sunlight also changes with the seasons. Because the Earth is tilted, different regions receive more direct sunlight at different times of the year. When one hemisphere tilts toward the sun, it experiences longer days and more direct light. This leads to warming. When it tilts away, days become shorter, and sunlight arrives at a lower angle. This leads to cooling. These seasonal changes are gradual, but they influence large-scale weather patterns. The distribution of energy shifts, and the atmosphere adjusts. It is important to notice that the sun does not heat the air directly in most cases. Instead, it heats the surface of the Earth. The surface then transfers heat to the air above it. This transfer happens through conduction and through convection. Conduction is the direct transfer of heat from a warm surface to the air touching it. Convection involves movement. Warm air rises, and cooler air replaces it. This creates vertical circulation, radiation, conduction, and convection. These are the main ways energy moves. They work together, continuously. As warm air rises, it carries energy upward. As it rises, it expands due to lower pressure. This expansion causes cooling. This cooling can lead to condensation. If moisture is present, This is how clouds begin to form. In this way, the sun's energy is linked to cloud formation. Even though the process is indirect, the atmosphere also loses energy. It radiates heat back into space. This balance between incoming and outgoing energy helps regulate temperature. If more energy enters than leaves, the system warms. If more leaves than enters, the system cools. At any moment, this balance is shifting slightly, and the atmosphere responds. Clouds play a role in this balance. They can reflect sunlight, reducing heating. They can also trap outgoing heat, slowing cooling. Their effect depends on their type and their altitude. Again, the system is interconnected. Nothing acts in isolation. Over larger scales, the uneven heating of the Earth drives global circulation. Warm air rises near the equator and moves poleward at higher altitudes. Cooler air moves toward the equator near the surface. This creates large looping patterns, known as circulation cells. These patterns help move energy around the planet. They also influence wind patterns and weather systems. Even though these movements are large, they follow the same basic rule. Energy flows from areas of higher concentration to areas of lower concentration. This flow is never perfectly even, and so motion continues. It can be helpful to pause here and rest with a simple idea. The sun provides energy. That energy is unevenly distributed, and that uneven distribution creates movement. This pattern repeats at every scale, from small breezes to global winds. The details may change, but the principle remains steady. By holding on to this idea, we can approach more complex behavior without confusion. As we continue, we will look more closely at how this energy and these temperature differences translate into pressure changes and the movement of air we feel as wind. Air is always in motion, even when it feels still. This motion is driven by differences, especially differences in temperature and pressure. To understand wind, we begin with pressure. Air has mass, and because of that mass, it exerts force on surfaces. This force is called air pressure. At the surface of the Earth, we are under the weight of the entire atmosphere above us. This pressure is not the same everywhere. It changes from place to place. These differences are small, but they are enough to move air. Pressure differences form when air is heated unevenly. Warm air expands and becomes less dense. As it expands, it rises. When air rises, it reduces the amount of air pressing down on the surface below. This creates an area of lower pressure. In contrast, cool air contracts and becomes more dense. It tends to sink. When air sinks, it increases the amount of air pressing down on the surface. This creates an area of higher pressure. These rising and sinking motions happen continuously across the planet. As a result, the atmosphere is filled with regions of relatively high pressure and relatively low pressure. Air moves in response to these differences. It flows from areas of higher pressure toward areas of lower pressure. This movement is what we call wind. The greater the pressure difference, the stronger the wind. This relationship is steady and predictable. Pressure differences create a force, known as the pressure gradient force. This force pushes air across the surface of the Earth. But wind does not move in a straight line for long. Other factors influence its path. One of these is the rotation of the Earth. As the Earth spins, moving air is deflected. This deflection is called the Coriolis effect. In the northern hemisphere, moving air is deflected to the right. In the southern hemisphere, it is deflected to the left. This does not create wind, but it changes its direction. As a result, winds often curve, rather than moving directly from high to low pressure. Another influence is friction. Near the surface, air moves across land, water, and obstacles. Trees, buildings, and terrain slow the motion of air. This reduces wind speed and alters direction slightly. Higher in the atmosphere, where there is less friction, winds can move more freely. This is why strong winds often occur at higher altitudes. When we combine these effects, pressure gradient, Coriolis deflection, and friction, we begin to see how wind patterns form. Air does not simply rush inward. It often flows along curved paths around areas of high and low pressure. Areas of low pressure are often associated with rising air. As air rises, it can cool, and moisture may condense. This can lead to cloud formation and precipitation. For this reason, low-pressure systems are often linked with unsettled weather. Areas of high pressure are different. Here, air is generally sinking. As it sinks, it warms and becomes drier. This tends to suppress cloud formation. As a result, high-pressure systems are often associated with clearer skies. These patterns are not absolute, but they are common. The movement of high and low-pressure systems across the surface helps shape daily weather changes. As one system replaces another, conditions shift. Temperature changes, cloud cover changes, wind direction changes. All of these are connected. It is helpful to think of pressure as a field spread across the surface of the earth with gentle slopes rather than sharp drops. Air flows down these slopes from higher pressure toward lower pressure. The steeper the slope, the faster the flow. Meteorologists map these patterns using lines called isobars. Each line connects points of equal pressure. Where isobars are close together, the pressure gradient is strong. Winds are usually stronger there. Where isobars are spaced farther apart, the gradient is weaker. Winds tend to be lighter. This visual approach helps describe the invisible structure of the atmosphere. Wind also transports energy. It moves warm air into cooler regions and cool air into warmer regions. This process helps reduce temperature differences. But it also creates new patterns as air masses interact. An air mass is a large body of air with relatively uniform temperature and moisture. When different air masses meet, they do not mix immediately. Instead, they form boundaries. These boundaries are called fronts. Along a front, weather can change more quickly. Clouds may form, winds may shift, precipitation may develop. Again, we see the same pattern. Differences lead to motion, and motion leads to change. Even on a small scale, this principle holds. For example, during the day, uneven heating of the ground can create small pressure differences. These can produce gentle local winds. At night, as the ground cools, these patterns may weaken or reverse. The system is always adjusting, always responding to energy changes. Wind is not separate from temperature or pressure. It is a direct result of them. When we feel wind, we are feeling the atmosphere working to restore balance. The movement may be gentle, or it may be strong. But the underlying cause is the same. This repetition is useful. It simplifies what might seem complex. Air moves because of differences. And those differences come from uneven heating. This idea connects back to the source of energy and forward to other processes. As air moves, it also carries moisture. Water vapor travels with the air, rising, cooling, and sometimes condensing. This brings us toward another essential part of weather: the continuous movement and transformation of water in the atmosphere. Let us now follow that movement. As water changes form and cycles through the system, water is always moving, even when we do not see it. It shifts between forms and between places in a continuous process. This process is called the water cycle. It connects the surface of the earth, the atmosphere, and back again. It is steady and it repeats. The cycle begins with evaporation. Liquid water absorbs energy, usually from the sun, and changes into water vapor. This change happens at the surface of oceans, lakes, rivers, and soil. It also happens from living things through a process called transpiration. Plants release water vapor into the air through small openings in their leaves. Together, evaporation and transpiration are often grouped as evapotranspiration. Both processes add moisture to the atmosphere. Evaporation requires energy, and that energy is stored in the water vapor. This stored energy is called latent heat. It is not felt directly, but it becomes important later. As water vapor rises, it moves with the air. This movement depends on wind and vertical motion. The vapor itself is invisible. It mixes with the surrounding air. The amount of water vapor the air can hold depends on temperature. Warm air can hold more moisture. Cool air can hold less. This relationship is steady and predictable. As air rises, it expands and cools. This cooling reduces the air's capacity to hold water vapor. When the air becomes saturated, condensation begins. Condensation is the process where water vapor changes back into liquid. This change releases the latent heat that was stored earlier. That released energy can warm the surrounding air slightly and influence further motion. Condensation does not happen in empty space. It requires small particles. These particles are called condensation nuclei. They can be dust, salt, or tiny aerosols in the air. Water vapor gathers around these particles, forming tiny droplets. Many of these droplets together form clouds. Clouds are made of either liquid droplets or ice crystals, or a mix of both. Their form depends on temperature and altitude. At this stage, the water is suspended in the air. It has not yet returned to the surface. For precipitation to occur, these droplets or crystals must grow larger. This growth happens through collisions and through the gathering of additional moisture. In warmer clouds, droplets collide and merge. In colder clouds, ice crystals can grow by collecting water vapor. Eventually, the particles become heavy enough. Gravity pulls them downward. This is precipitation. It can take different forms, depending on temperature. Rain forms when droplets remain liquid as they fall. Snow forms when ice crystals remain frozen. Sleet and hail involve more complex paths, through layers of varying temperature. Once precipitation reaches the ground, the cycle continues. Some water flows over the surface as runoff. It moves into streams, rivers, and eventually oceans. Some water soaks into the ground, becoming groundwater. This stored water can return slowly, through springs or plant uptake, and then back into the atmosphere. The cycle does not have a fixed beginning or end. It is continuous. It operates at many scales, from a small pond to the entire planet. At every stage, energy is involved. Evaporation absorbs energy. Condensation releases it. This exchange connects the water cycle to atmospheric motion. When large amounts of condensation occur, such as in cloud formation, the released heat can strengthen rising air. This can influence weather systems, making them more active. Humidity is a measure of how much water vapor is in the air. It can be expressed in different ways, but the idea remains simple. Higher humidity means more moisture. Lower humidity means less. Relative humidity compares the current amount of vapor to the maximum the air can hold at that temperature. When relative humidity reaches 100%, the air is saturated. This is when condensation becomes likely. Another useful idea is the dew point. This is the temperature at which air becomes saturated. If air cools to this point, condensation begins. This can happen near the ground, forming dew, or higher in the atmosphere, forming clouds. Again, the pattern is consistent. Temperature changes affect moisture, and moisture changes affect weather. The water cycle is not separate from air movement. It depends on it. Wind transports water vapor from one region to another. Rising air helps form clouds. Sinking air can reduce them. In dry regions, evaporation may exceed precipitation. In wet regions, precipitation may be more frequent. These differences create varied climates. But the underlying cycle remains the same. It is steady and continuous. By returning to the core steps, we keep clarity. Evaporation adds moisture. Condensation forms clouds. Precipitation returns water to the surface. Each step follows from the one before, and each step depends on energy and temperature. This repetition is useful. It simplifies a complex system. It allows us to understand many different weather patterns through the same structure. As we continue, we will focus more closely on clouds themselves, how they form, how they take shape, and what their different forms can tell us about the atmosphere. Clouds are visible signs of processes we cannot see directly. They show where air is rising, cooling, and reaching saturation. Each cloud is made of many tiny droplets, or ice crystals, held in the air by upward motion. They are not solid objects. They are collections of suspended particles. Their shape and structure depend on conditions in the atmosphere, especially temperature, moisture, and vertical motion. By observing clouds, we can infer what the air is doing. A simple way to begin is by grouping clouds by their height and by their form. Height tells us where in the atmosphere the cloud exists. Form tells us how the air is moving. We start with high clouds. These form at altitudes typically above 6 kilometers. At these heights, temperatures are low, so clouds are usually made of ice crystals. One common type is cirrus. Cirrus clouds are thin and wispy. They often appear as streaks or fine threads across the sky. They form where air is moving gently upward and spreading out. Cirrus clouds do not produce precipitation that reaches the ground, but they can indicate changes in the atmosphere. Their presence sometimes suggests that a larger system is approaching. Another high cloud type is cirrostratus. These clouds form thin layers, covering large areas of the sky. They can create a halo effect around the sun or moon. This happens because ice crystals bend light. Cirrostratus clouds also do not usually produce precipitation, but they are part of broader patterns. We then move to mid-level clouds. These form between about 2 and 6 kilometers. Temperatures here are lower than at the surface, but not always cold enough for only ice. These clouds can contain both liquid droplets and ice crystals. Altostratus clouds are one example. They appear as gray or bluish layers, often covering the sky. The sun may be visible, but dimmed. These clouds are associated with widespread lifting of air, often ahead of larger weather systems. Another mid-level type is altocumulus. These clouds appear as rounded patches or clusters. They can form in patterns, sometimes with shadows. Altocumulus clouds suggest some instability in the air, though not always strong enough to produce storms. Next are low clouds. These form below about 2 kilometers. At these heights, temperatures are usually warmer, so clouds are mainly composed of liquid droplets. Stratus clouds are a common low-level type. They form uniform gray layers, often covering the sky completely. They can produce light precipitation, such as drizzle. Stratus clouds are associated with stable conditions and gentle lifting. Another low cloud is stratocumulus. These appear as low, lumpy layers. They often have breaks, allowing some sunlight through. Stratocumulus clouds usually do not produce heavy precipitation, but they can influence temperature by limiting sunlight during the day and reducing cooling at night. Beyond height, clouds can also be understood by their vertical development. Some clouds grow upward through large portions of the troposphere. These are called cumuliform clouds. The most familiar is cumulus. Cumulus clouds appear as distinct, puffy shapes with flat bases and rounded tops. They form when warm air rises in localized areas. As the air rises, it cools and condensation begins. The flat base marks the level where saturation is reached. The rising motion continues above, building the cloud upward. Small cumulus clouds often indicate fair weather. But if the upward motion is strong, these clouds can grow larger. They can develop into cumulonimbus clouds. Cumulonimbus clouds are tall and vertically developed. They can extend from low levels up to the tropopause. Their tops often spread out, forming an anvil shape. These clouds are associated with thunderstorms, heavy rain, and strong winds. They form when rising air is strong and sustained. This upward motion is driven by instability, when warm air near the surface rises rapidly into cooler air above. Again, the same pattern appears. Rising air cools. Cooling leads to condensation. Condensation releases energy. And that energy can support further rising. This feedback allows clouds to grow. Cloud shapes are not random. They reflect the structure of the atmosphere. Layered clouds suggest stable air, where vertical movement is limited. Towering clouds suggest unstable air, where vertical motion is strong. By observing shape, we gain insight into motion. Cloud coverage also matters. A clear sky allows more sunlight to reach the surface. This can lead to warming during the day. At night, clear skies allow heat to escape more easily. This can lead to cooling. Clouds change this balance. They can reflect incoming sunlight, and they can trap outgoing heat. The effect depends on cloud type, thickness, and altitude. High, thin clouds may allow sunlight through, while reducing heat loss. Low, thick clouds may block sunlight and keep temperatures more stable. Again, we see interaction. Clouds are part of the energy balance, not separate from it. Clouds are also temporary. They form when conditions allow, and they dissipate when conditions change. If rising motion weakens, or if the air becomes drier, droplets may evaporate. The cloud fades and disappears. This constant forming and dissolving reflects the dynamic nature of the atmosphere. By returning to simple ideas, we maintain clarity. Clouds form when air rises and cools. Their type depends on height, temperature, and motion. Their presence indicates moisture and movement. This repetition helps us read the sky, not as random shapes, but as structured signals. As clouds grow and change, they may begin to produce precipitation. Droplets increase in size, ice crystals develop, and gravity begins to act more strongly. This leads us naturally to the next step in the process: the conditions under which clouds release water back to the surface in the form of rain, snow, or other types of precipitation. Precipitation begins when particles in a cloud become large enough to fall. This is a gradual process, built from many small interactions. Clouds contain tiny droplets, or ice crystals. Each one is very light. On their own, they remain suspended in rising air. But over time, they grow. This growth is essential. Without it, precipitation would not occur. There are two main pathways for this growth. One occurs in warmer clouds, and one in colder clouds. We begin with warm clouds. These are clouds where temperatures remain above freezing. In these clouds, droplets grow through collision and coalescence. Collision means droplets meet. Coalescence means they combine. Larger droplets fall slightly faster than smaller ones. As they fall, they collect more droplets. This process repeats, slowly building size. Over time, some droplets become heavy enough. Gravity begins to overcome upward motion, and they fall as rain. This process is common in tropical regions, where clouds are warm and deep. The second pathway occurs in cold clouds, where temperatures are below freezing. In these clouds, both ice crystals and supercooled water droplets can exist. Supercooled droplets are liquid, even below 0 degrees Celsius. They remain liquid because they lack a surface to freeze on. Ice crystals grow differently. Water vapor deposits directly onto them. This process is called deposition. The key idea is that vapor prefers to attach to ice rather than remain as liquid droplets. This causes ice crystals to grow at the expense of nearby droplets. As the crystals grow, they become heavy. They begin to fall. This is known as the Bergeron process. It is a major mechanism for precipitation in mid-latitude regions. As particles fall through the cloud, they may continue to grow. They may collect more droplets or collide with other crystals. Their final form depends on the temperature of the air they pass through. If the air below is warm, ice crystals may melt and fall as rain. If the air remains cold, they may reach the ground as snow. Snowflakes are collections of ice crystals joined together. Their shape depends on temperature and humidity. Patterns can vary, but all follow the same physical principles. Sometimes, precipitation falls through layers of air with different temperatures. This can produce mixed forms. For example, Snow may melt into rain, and then refreeze into ice pellets. This is called sleet. In other cases, rain may fall through a shallow, cold layer and freeze upon contact with surfaces. This produces freezing rain. Hail forms in strong storm clouds, where upward motion is intense. In these clouds, particles are carried upward repeatedly. Each cycle adds a new layer of ice. As the particle grows, it eventually becomes too heavy and falls to the ground. Hail requires strong updrafts and significant vertical development. Precipitation is not only about falling particles. It also reflects the structure of the atmosphere. Steady, widespread precipitation often comes from layered clouds, such as nimbostratus. These clouds form in stable conditions, with broad lifting of air. The result is continuous, moderate rain or snow. In contrast, intense precipitation often comes from cumulonimbus clouds. These clouds form in unstable conditions, with strong upward motion. The result is heavier, more localized precipitation, sometimes with rapid changes. The intensity of precipitation depends on several factors: the amount of moisture in the air, the strength of upward motion, and the depth of the cloud. More moisture allows more droplets to form. Stronger upward motion supports larger particles. Deeper clouds provide more space for growth. All of these contribute to how much precipitation reaches the ground. Not all precipitation reaches the surface. Sometimes, falling droplets evaporate before they arrive. This is called virga. It occurs when the air below the cloud is dry. The droplets shrink and disappear, leaving visible streaks beneath the cloud. This again shows the role of moisture and temperature. Precipitation also redistributes energy. When water changes phase, energy is absorbed or released. As droplets form, heat is released. As they evaporate, heat is absorbed. These exchanges influence local conditions and can affect air movement. The cycle continues after precipitation reaches the ground. Water may flow, soak, or evaporate again. Each path leads back into the system. This reinforces the idea of continuity. Nothing is isolated. Every drop is part of a larger process. By returning to the basic sequence, we keep understanding steady. Particles form in clouds. They grow. They fall when heavy enough. Their form depends on temperature, and their path depends on the air they move through. This pattern repeats across different regions and across different conditions. Precipitation is not sudden. It is the result of gradual change. Many small steps leading to a visible outcome. As these processes become more intense and more organized, they can lead to stronger weather events. Systems where rising air, moisture, and energy interact more actively. This leads us toward a deeper look at storms and how the atmosphere transitions from steady patterns into more concentrated forms of motion and release. Storms form when the same basic processes become more concentrated and more organized. The principles do not change, but their intensity increases. Air still rises. Moisture still condenses. Energy is still transferred. But these processes happen more rapidly and over greater vertical distances. A storm begins with instability. Instability occurs when warm air near the surface lies beneath cooler air above. This arrangement allows air to rise freely. Once lifted, the warm air continues to rise because it remains less dense than its surroundings. This upward motion is the foundation of many storms. As air rises, it cools, and water vapor condenses. Clouds form and grow vertically. When the rising motion is strong enough, these clouds develop into cumulonimbus. These are the clouds most often associated with thunderstorms. Within a cumulonimbus cloud, air is moving both upward and downward. The upward currents are called updrafts. The downward currents are called downdrafts. Updrafts carry warm, moist air upward. Downdrafts bring cooler air downward. This internal circulation sustains the storm. As condensation occurs, latent heat is released. This added energy can strengthen the updraft, allowing the cloud to grow taller. The stronger the updraft, the more moisture it can carry, and the more energy can be released. This creates a feedback loop that supports storm development. Eventually, precipitation begins to form within the cloud. As droplets and ice particles grow, they begin to fall. This falling motion contributes to downdrafts. As rain or hail descends, it drags air downward with it. This creates a flow of cooler air toward the surface. When this air reaches the ground, it spreads outward, sometimes producing gusty winds. Thunderstorms often include lightning. Lightning is an electrical discharge. It occurs when charges build up within the cloud. Collisions between ice particles can separate positive and negative charges. Over time, this separation becomes strong enough to overcome the resistance of the air. A sudden discharge occurs, equalizing the charges. This is lightning. The rapid heating of air during a lightning strike causes expansion. This expansion produces a sound wave, which we hear as thunder. The sequence is consistent: lightning first, then thunder, though the delay depends on distance. Storms vary in size and duration. Some are short-lived, lasting less than an hour. Others organize into larger systems, lasting many hours or longer. The structure of the atmosphere and the availability of moisture influence this development. In some cases, storms form along boundaries between air masses. These boundaries are called fronts. When warm air meets cooler air, it may be forced to rise. This lifting can trigger cloud formation and storm development. Cold fronts, where cooler air advances, often produce more abrupt lifting. This can lead to more intense storms. Warm fronts, where warm air rises over cooler air, tend to produce more gradual changes. Storms can also form without fronts, especially in regions with strong surface heating. During the day, the ground warms, warming the air above it. This air rises and can develop into isolated thunderstorms. These are often called air mass storms. They tend to be short-lived and localized. In stronger cases, storms can organize into systems with rotating motion. This rotation can occur when wind speed or direction changes with height. This change is called wind shear. When rising air interacts with shear, it can begin to rotate. This rotation can lead to more persistent and structured storms. In rare cases, this can produce tornadoes. Tornadoes are narrow, rotating columns of air, extending from a cloud to the ground. They form under specific conditions, involving strong instability and wind shear. While intense, they are localized and short-lived compared to larger systems. Another type of storm occurs over warm ocean waters. These are tropical cyclones. They form when ocean temperatures are high, providing abundant moisture and energy. Warm, moist air rises and condenses, releasing heat. This process lowers pressure at the surface, drawing in more air. As air flows inward, it begins to rotate due to the Coriolis effect. This rotation organizes the system, creating a large-scale storm with a defined structure. At the center, there may be a region of relatively calm conditions, known as the eye. Surrounding it are bands of clouds and precipitation. These systems can persist as long as they remain over warm water and maintain their energy source. When they move over land or cooler water, they tend to weaken. Across all types of storms, the same core ideas apply. Instability allows air to rise. Moisture provides material for clouds, and energy drives motion. When these elements combine, storms can form. When they weaken, storms dissipate. The system returns to a more stable state. Storms are not separate from the rest of the atmosphere. They are part of its effort to redistribute energy. They move heat, moisture, and momentum across regions. This movement contributes to larger patterns that extend beyond individual events. By observing storms, we see the same processes in a more active form. Rising air, cooling, condensation, precipitation. Each step remains consistent. Only the scale and intensity change. This repetition provides clarity, even as the system becomes more complex. As storms form and move, they are guided by larger patterns in the atmosphere. These patterns influence where storms travel and how they evolve. To understand that movement, we turn to the broader circulation of the atmosphere and the large-scale flows that shape weather across the planet. Across the planet, the atmosphere moves in large patterns. These patterns are steady over time, but always in motion. They redistribute energy from warmer regions to cooler ones. This movement is not random. It follows structure. And that structure is shaped by uneven heating. The equator receives more direct sunlight. The poles receive less. This difference creates a global temperature gradient. The atmosphere responds by moving air in large looping patterns. These loops are called circulation cells. There are three main types in each hemisphere: the Hadley cell, the Ferrel cell, and the polar cell. We begin near the equator, where sunlight is strongest. Here, air warms and rises. This rising motion creates a region of low pressure. As the air rises, it cools, and moisture condenses. This leads to frequent cloud formation and precipitation. This region is often called the intertropical convergence zone. Rising air cannot continue upward indefinitely. It spreads outward at higher altitudes. As it moves away from the equator, it gradually cools further. Eventually, it begins to sink, around 30 degrees latitude. This sinking air creates regions of higher pressure. Sinking air warms as it compresses, reducing relative humidity. This suppresses cloud formation and leads to drier conditions. Many of the world's deserts are located in these regions. This entire loop, rising near the equator, moving poleward, sinking at subtropical latitudes, and returning toward the equator near the surface, is called the Hadley cell. Near the surface, the returning air does not move straight north or south. It is deflected by the rotation of the Earth. This creates the trade winds. In the northern hemisphere, they blow from the northeast. In the southern hemisphere, from the southeast. These winds converge near the equator, reinforcing rising motion. Moving poleward from the Hadley cell, we enter the Ferrel cell. This cell operates between about 30 and 60 degrees latitude. It is less direct than the Hadley cell and is influenced by interactions between air masses. Near the surface, air flows poleward from the subtropical high-pressure regions. This air is deflected, creating the westerlies. These winds blow from west to east. They are common in mid-latitude regions and influence many weather systems. As this air moves poleward, it eventually meets colder air from higher latitudes. This meeting occurs near the polar front. Here, air is forced to rise, leading to cloud formation and precipitation. Above this region, air flows equatorward at higher altitudes, completing the Ferrel cell. The third cell is the polar cell. It operates near the poles. Here, air is cold and dense. It tends to sink. This creates high-pressure conditions at the surface. From these regions, air flows toward lower latitudes. As it moves, it is deflected, forming the polar easterlies. These winds blow from east to west. When this cold air meets warmer air from the Ferrel cell, it rises, creating a boundary zone. This interaction contributes to weather activity in mid-latitudes. Together, these three cells form a global circulation pattern. Energy is transported from the equator toward the poles through this system. But this circulation is not perfectly smooth. It is influenced by land, oceans, and seasonal changes. Continents heat and cool differently than oceans. This creates variations in pressure and modifies wind patterns. Mountains can block or redirect airflow, creating local changes within the larger system. Another important feature of large-scale circulation is the jet stream. Jet streams are narrow bands of fast-moving air, found near the boundaries between circulation cells. The most prominent is the polar jet stream. It forms near the boundary between the Ferrel and polar cells. Here, temperature differences are strong, creating a steep pressure gradient. This drives fast winds at high altitude. The jet stream does not move in a straight line. It meanders, forming waves. These waves influence the movement of weather systems. They can guide storms and separate warm and cold air masses. When the jet stream shifts, weather patterns shift with it. This connection is consistent and observable. Large-scale circulation also interacts with the oceans. Ocean currents move heat across the planet. These currents influence air temperature above them and can affect weather patterns. For example, Warm ocean currents can increase moisture in the air, while cold currents can stabilize it. This interaction reinforces the idea that Earth's systems are connected. Atmosphere and ocean work together to redistribute energy. Seasonal changes also shift these patterns. As the sun's direct rays move north and south, the zones of rising and sinking air shift with them. This causes circulation cells to adjust and wind patterns to move slightly. The result is a gradual change in weather over the year. Despite these variations, the overall structure remains stable. Energy flows from regions of higher input to regions of lower input. Air moves in response, forming repeating patterns. By returning to this core idea, we maintain clarity. Uneven heating creates differences. Differences create motion, and motion organizes into patterns. These patterns shape weather across large distances. They guide storms, influence temperatures, and determine prevailing winds. Even though we experience weather locally, it is part of this global system. The atmosphere connects distant regions through continuous movement. Understanding this connection allows us to see weather not as isolated events, but as part of a larger structure. As these patterns shift slowly over time, they create the changes we recognize as seasons. Differences in sunlight and energy distribution, leading to gradual changes in temperature and weather patterns across the year. Over the course of a year, weather follows a gradual rhythm. This rhythm is shaped by the position of the Earth relative to the Sun. The Earth is tilted on its axis by about 23.5 degrees. This tilt is constant as the Earth orbits the Sun. It does not change direction, only its position in space. Because of this, different parts of the Earth receive different amounts of sunlight throughout the year. This variation creates the seasons. When one hemisphere is tilted toward the sun, sunlight strikes it more directly. Days become longer, and more energy is received. This leads to warming. At the same time, the opposite hemisphere is tilted away. Sunlight arrives at a lower angle and for a shorter duration. This leads to cooling. These changes are gradual. They unfold over weeks and months. The transition between seasons is not sudden. It is continuous. At the equator, seasonal changes are smaller. Sunlight remains relatively direct throughout the year. Temperatures vary less, and day length changes only slightly. At higher latitudes, seasonal differences become more pronounced. In summer, days are long, and sunlight is more direct. In winter, days are short, and sunlight is weaker. Near the poles, this effect becomes extreme. There can be continuous daylight in summer, and continuous darkness in winter. The distribution of energy changes with these shifts, and the atmosphere responds. As regions warm, air tends to rise. As regions cool, air tends to sink. This alters pressure patterns and influences wind. The large-scale circulation adjusts slightly, moving zones of rising and sinking air north and south. The intertropical convergence zone shifts position, following the region of strongest heating. This movement affects rainfall patterns, especially in tropical regions. Wet and dry seasons often result from this shift. In mid-latitudes, seasonal changes influence the strength and position of the jet stream. In winter, temperature differences between equator and poles are greater. This strengthens the jet stream and can lead to more active weather patterns. In summer, these differences are smaller. The jet stream weakens and may shift poleward. This can lead to more stable conditions in some regions. Land and water respond differently to seasonal heating. This creates additional variation. Land warms and cools more quickly, while oceans change temperature more slowly. This difference can influence pressure patterns and wind direction. In some regions, this leads to seasonal wind systems. One example is the monsoon. During warmer months, land heats more than nearby oceans. Air rises over land, creating lower pressure. Moist air from the ocean flows inward. This brings increased rainfall. During cooler months, the pattern reverses. Land cools more quickly, creating higher pressure. Air flows outward toward the ocean. This reduces rainfall. Again, the pattern is consistent. Differences in heating create differences in pressure, and those differences drive motion. Seasonal changes also influence ecosystems. Vegetation responds to temperature and sunlight. Snow and ice cover can expand or retreat. These changes affect how much energy is absorbed or reflected. For example, snow reflects a large portion of sunlight. This can reinforce cooling. As snow melts, darker surfaces are exposed, absorbing more energy. This can reinforce warming. These feedbacks add complexity, but they follow the same underlying principles. Energy input changes. The system responds. Over time, these responses create the patterns we recognize as seasons. It is helpful to return to a simple idea. The Earth's tilt changes how sunlight is distributed, and this distribution shapes temperature. Temperature differences influence pressure, and pressure differences move air. This sequence repeats throughout the year. Even though each day's weather may vary, It is part of this larger cycle. Seasons provide a framework within which weather operates. They do not determine exact conditions, but they influence the range of possibilities. For example, winter conditions increase the likelihood of snow. Summer conditions increase the likelihood of convective storms. These tendencies reflect underlying energy patterns. As the Earth continues its orbit, the cycle repeats. The same positions relative to the Sun occur each year, but the exact weather can still vary because of interactions within the atmosphere. This balance between repetition and variation is a defining feature of weather. The structure remains stable, while the details shift. By holding onto the structure, we can understand the variation. As we continue, we will look at events where these patterns become more extreme. Situations where the same processes lead to stronger, less frequent outcomes. And how these events still follow the same underlying principles. Sometimes the atmosphere produces events that feel more intense, yet they follow the same structure. The same principles remain in place. Only the magnitude changes. These are often called extreme weather events. They include heat waves, cold spells, droughts, floods, and powerful storms. Each one can be understood by returning to simple ideas: energy, moisture, and motion. We begin with heat waves. A heat wave is a period of unusually high temperatures. It often occurs when a region of high pressure remains in place. This is sometimes called a blocking pattern. Under high pressure, air tends to sink. Sinking air warms as it compresses. Clouds are less likely to form, allowing more sunlight to reach the surface. This increases heating during the day. At night, limited cloud cover can allow heat to escape. But if the air remains warm, cooling is reduced. Over several days, heat can build. The key idea remains simple. Reduced cloud cover and persistent sinking air lead to sustained warming. Cold spells follow a similar pattern, but with different conditions. They occur when cold air masses move into a region or remain in place for extended periods. This can happen when circulation patterns shift, allowing polar air to move toward lower latitudes. Under clear skies and light winds, heat can escape efficiently from the surface. This leads to further cooling. Again, the process is gradual. Energy is lost, and temperature decreases over time. Droughts develop when precipitation is reduced over a long period. This often involves persistent high-pressure systems, which limit cloud formation and reduce rainfall. Without regular precipitation, soil moisture decreases. Evaporation continues, but is not balanced by incoming water. Over time, the land becomes drier. Vegetation may be affected, and local temperatures can increase. This is because dry soil heats more quickly. The system reinforces itself through feedback. Floods represent the opposite condition. They occur when precipitation exceeds the ability of the ground and waterways to absorb or carry water. This can result from prolonged rainfall or intense short-term events. When soil is already saturated, additional water becomes runoff. Rivers may rise and overflow their banks. The underlying principle remains the same. Moisture input exceeds the system's capacity to redistribute it, leading to accumulation. Strong storms can also produce extreme conditions, such as high winds, heavy rainfall, or hail. These arise when instability, moisture, and lifting are all present at high levels. The processes we have described earlier become more active. Updrafts are stronger, clouds grow taller, and precipitation forms more rapidly. The same steps occur, but more quickly. Tropical cyclones are another example. They represent a large-scale organization of these processes. Warm ocean water provides energy through evaporation. Rising air leads to condensation, releasing heat. This heat fuels further rising motion. The system becomes organized and rotates. As long as the energy source remains, the system can persist. Once again, the same principles apply. Energy input, moisture availability, and atmospheric motion. Extreme events are often influenced by blocking patterns. These occur when large-scale circulation becomes slow or stationary. This can cause weather systems to remain in one place. When a system remains, its effects accumulate. Heat waves last longer. Rainfall continues over the same area, or dry conditions persist. The key idea is duration. The longer a pattern remains, the greater its impact. Another factor is variability. The atmosphere naturally fluctuates. Some periods bring more moisture, others bring less. Some bring warmer air, others bring cooler air. Extreme events often occur at the edges of this variability. When conditions move beyond the typical range. Yet even at these extremes, the system does not change its rules. It follows the same relationships between temperature, pressure, and motion. It is also important to note that local factors can influence outcomes. Topography can affect airflow. Proximity to water can influence moisture. Urban areas can alter temperature patterns. These factors do not replace the larger system. but they modify how it is expressed in specific locations. By returning to a simple structure, we can understand these events clearly. When energy accumulates, temperatures rise. When energy is lost, temperatures fall. When moisture is abundant, precipitation increases. When motion is strong, systems intensify. These relationships are steady, even when the outcomes are extreme. This repetition provides a stable framework for understanding change. Extreme weather is not separate. It is an extension of everyday processes. The same mechanisms, operating under different conditions. As we continue, we bring these ideas together, forming a complete picture of how weather works, from small-scale interactions to global patterns, and how these layers connect into a single continuous system. Weather can appear complex, but its structure is consistent across scales. From a small cloud to a global pattern, the same processes repeat. Energy enters the system, mainly from the sun. This energy is unevenly distributed, creating differences in temperature. Temperature differences lead to differences in pressure, and pressure differences drive motion. This motion moves air, and with it, moisture. When air rises, it cools. When it cools, water vapor condenses. Clouds form. When droplets or ice crystals grow large enough, they fall. This is precipitation. When air sinks, it warms. Warming reduces relative humidity. Clouds become less likely. This sequence is steady and continuous. By returning to it, we can understand many different weather events. Local weather reflects immediate conditions: temperature, humidity, and wind. But these conditions are shaped by larger patterns. Air masses move, carrying their properties with them. Boundaries between air masses create zones of change. Lifting occurs, clouds form, and precipitation can follow. At the same time, global circulation redistributes energy, moving warmth toward the poles and cooler air toward the equator. This circulation is shaped by the rotation of the Earth and by the distribution of land and water. It creates prevailing wind patterns and guides weather systems. Seasonal changes add another layer. The tilt of the Earth alters how sunlight is distributed. Regions receive different amounts of energy over time. This shifts temperature patterns and influences pressure. Circulation adjusts, and weather patterns move. Over the year, this produces the cycle of seasons. Within this framework, variability remains. The atmosphere is dynamic. Small changes can influence outcomes. Yet even with variation, the structure holds. Storms form when instability, moisture, and lifting combine. Clouds grow vertically. Precipitation intensifies. Wind patterns shift, and energy is redistributed. When these processes weaken, conditions return to a more stable state. Extreme events follow the same rules. They occur when certain factors become more pronounced. Heat waves form under persistent high pressure. Droughts develop when precipitation is limited. Floods occur when moisture input exceeds capacity. Storms intensify when energy and motion align. In each case, the underlying relationships remain unchanged. This consistency allows us to build understanding, step by step. It also allows us to observe patterns and anticipate likely outcomes. Observation is an important part of understanding weather. By watching the sky, we can see cloud types. By feeling the air, we notice temperature and humidity. By observing wind, we detect motion. These observations connect directly to the processes we have described. A rising cloud indicates upward motion. A clear sky suggests sinking air. Steady rain reflects widespread lifting. Sudden changes in wind can indicate shifting pressure patterns. Each observation fits into the larger structure. Over time, patterns become familiar. Repetition builds understanding. This understanding does not remove complexity, but it provides a stable way to interpret it. It allows us to see weather as a system, rather than isolated events. A system with inputs, processes, and outputs. Energy enters. Motion redistributes it, and the atmosphere adjusts continuously. This adjustment never stops. Even in calm conditions, processes are still active. Air is still moving. Moisture is still changing phase. Energy is still being exchanged. By returning to these core ideas, we maintain clarity. Uneven heating creates differences. Differences create motion. Motion drives changes in moisture. And these changes produce the weather we experience. This cycle is continuous and interconnected. It links the surface of the earth, the oceans, and the atmosphere. It operates across timescales, from minutes to seasons, and across spatial scales, from local to global. Understanding weather is not about memorizing isolated facts. It is about recognizing patterns. Patterns that repeat and build upon one another. When we observe carefully and return to simple principles, the system becomes clearer. Not simpler in detail, but more understandable in structure. This steady structure remains, even as conditions change. And it is this structure that allows us to make sense of the quiet, continuous motion of the atmosphere.